So in the morning session, we saw how two Docker containers can talk to each other on a single machine, right? So you ran two network namespaces and you're able to connect them using a bridge. That's what Docker does for a single machine. But now we are kind of going into the world of Kubernetes, right? You don't have one machine anymore. You have a lot of machines, right? And so now you have containers running on multiple machines and they all have to connect to each other, right? That's your challenge. So this is what we saw today morning. There is a single host, multiple containers going via a Docker 0 bridge, right? We are all good with this. But now that you have multiple hosts, multiple workers, that trick doesn't work anymore, right? You can have that, but that is only useful for the containers within one worker. The moment two containers across workers have to talk to each other, something special has to be done. Why should something special has to be done, right? Because the containers have their own IPs, right? This is a different IP range than the one that the worker has. So in this example that we have here, so containers here have is 10.0.IP series, but the worker itself has a 10.100.IP series, right? So that cluster, that is the workers and the routers and the switches that make up that cluster, that hardware is aware only of this 100 series, right? That's what its job is. It was never meant to manage routing between these new things that you introduced, right? So that it is not its job. Somebody else has to do that job, right? That's where this CNI comes. Now, how would you, when you have containers on different workers, how do you get them to talk to each other, right? So you have two broad families of solutions. So one is tunneling, like VXLAN, and other is like, essentially in tunneling, you are doing something so that the routers between the workers are unaware, right? So they are not disturbed. But if you have control on those routers, then you can actually do some other family of techniques like BGP, which is basically using the full potential of the underlying routers. So what is tunneling? Has anyone heard the word tunneling in the context of networks? So essentially, in what you're doing is, every packet is anyway, if you know, it's a header and it's a payload, right? So what's inside the payload is not of interest to that layer. So when you have an L2 packet, there is an L2 frame header on both sides, and the thing inside is data, right? The L2 packet, the L2 layer doesn't care about that, what is there in it, right? It's just binary bytes. Right? Now, the layer above that actually makes sense of the data, and it's able to say that some portion of it is an header, IP header, and the rest of it is data, right? Again, it does the same thing. It doesn't care about the data, it just gives it to the higher layers, right? So everybody does this. They don't care about the data portion, they only care about the header portion. So what this allows us to do is, this allows us to transport a packet inside a packet, right? So like this image is trying to show. Both of these are vehicles, but instead of running the car on the road, you're just putting the car on the truck and letting the truck go, right? So you're just kind of putting the packet inside another packet, right? That's what we're doing with tunneling. That's what tunneling is. So there are a number of tunneling protocols. Okay. So there are a number of tunneling protocols. These are like, they have different header formats, they're different in terms of efficiency. Some are more useful in some context. You can just look into this later if you're interested. Today we'll be running one CNI called Flannel, which uses VXLAN, right? So you can, if our hands-on works very well, we'll be able to see the VXLAN packet. You'll be able to see the packet inside the packet, right? That's what you'll be able to see. So doing this packet inside packet, the outer network is not worried about the inside packet. The inside packets are actually from the container to the other container, right? The outer packets are actually from the worker to the other worker. That's what is the setup. So if you have to do this in Kubernetes, you have to set up this tunnel between the Kubernetes workers, and then the containers can talk to each other through those tunnels, right? So that's the idea of this encapsulation. So like I said, the other family of protocols this is just for your information, right? So there's this thing called BGP, and this kind of BGP is what runs the internet, right? So if you look at the internet as a whole, you have different internet service providers. Some of you get it from Airtel, some of you get it from Vodafone, etc., etc. So they have their own infrastructure, they have their own, all of their machines and their routers and their switches. Those things, if they don't connect to each other, right, you and I will never be able to talk over the internet, right? So that's what the BGP actually, it's the backbone of the internet actually. And you don't have to use that protocol just at the internet scale, you can actually use it for your personal cluster also. So if you have 100 machines in a lab, you can actually use BGP to connect those. But to do this, you need support from the routers and switches that connect those machines, right? So in the case of Kubernetes, Calico is an example CNI. So what it does for you is if you create a Kubernetes cluster with 100 workers and set up Calico on it, and if your routers are supporting it, then your containers will be able to use BGP to talk to each other across the workers. So I think I don't even have to explain this, right? You have seen you have gone through the difficulty today morning, so you kind of understand these points. You have, even yesterday you were running a lot of pods, right? Pods are coming and going. When you are in a deployment, you have n number of replicas of the same container, same service, right? And then they have different IPs. The pods will go down, the IPs will get removed, new IPs will come up, right? So you clearly can't be doing this manual thing of creating VHs for each of them, creating IP address for each of them, all of that, right? So that's why CNI is that's the job of the CNI, right? It's a layer in the Kubernetes networking stack. It's basically the backbone of the Kubernetes networking stack. So it does all of this automatically for you, right? That's the point. So just to show you how it fits in this context, you have Kubernetes that you were seeing yesterday. You use the kube control command to communicate with the Kubernetes control plane. Internally, it is running one or more CNI plugins, and those CNI plugins actually talk to the underlying Linux machine, right? So today morning we ran commands directly, right? We ran the netns command directly. In this case, you don't do it. The CNI plugin will do it for you. It will create and it will add those. Well, exactly the things that we did today morning, it will do it for you, right? And this is the kind of middle layer, which is doing all of the networking. So there are a number of CNI plugins available out there. I just put a screenshot of like this huge ecosystem. They all provide different kind of features. You have this huge space of, what is it that you prioritize? Do you want security, right? Then you can go for a different CNI plugin with different kind of security bit for the network connections between the workers. No, maybe you prioritize performance, right? So you want something that is fast, you're okay with losing some security, right? You have a different CNI plugin that can do that for you, right? So there is a huge set of trade-offs, and you can have different solutions of how you move the packets between one worker and another worker, right? Within a worker, you already see. If two containers on the same worker, it will go to the local bridge and go to the next one, right? So that's very clear. But if it's across two workers, it has to go through one of these solutions, right? Either tunnel or BGP, something has to be set up, something has to be managed, and only then they can communicate. So I mentioned this today morning, I'll just repeat this again. There are 2 or 3 main important things that the CNI plugin has to do for you, right? It has to create the L2 interface. This is that E1, E2, B1, B2 that we are creating. So whenever a container comes up, it has to create, the CNI plugin is supposed to take care of this job. And then it has to create the IP address. You did that manually. It has to automatically assign. See, we added a manual thing, and I think some of you actually face problems because you use the same IP on both places. You can't reuse IPs, obviously, right? So the CNI plugin's job is to ensure that it's actually giving different IPs to all the containers. And the next final thing is to do the actual routing between the thing. Again, we added some routes, very simple routes we added, and even that was not working for some of us. You can imagine the complexity when you have hundreds of workers and things changing all the time. So this is again just to show you like a trade-off between a number of CNI plugins. There are 4 CNI plugins shown here and a number of different dimensions, right? Like how do you configure? What kind of encryption do they give? What kind of, what's their advantages? All sorts of things, right? I mentioned some keywords, you can see those keywords here as well. So the rest of this session is to actually show you how a CNI works manually, right? So normally you don't do this, Kubernetes will do all this underneath. You just create a pod, you're able to ping, right? But let's say we do it ourselves. We take a CNI plugin, we are not going to change that portion. We are going to run the CNI plugin for our containers, right? That's what we're going to do in today's session. So you can actually see close up how the CNI plugin is working, right? And what are all the things it does. So ideally what I wanted to do was actually pair you up into groups of 2 and show connectivity between a container and machine 1 to machine 2. But given the number of networking problems we have had and the VM and inside host and stuff, we're going to simplify this and instead have you run 2 containers which are going to act like workers for you, right? So for the rest of the session, we'll create 2 containers, A and B, and then you can kind of forget about Docker, right? Just think that A and B are 2 machines, right? Don't care how A and B are talking to each other. That's not your problem. Just forget the containers also, because we will be creating containers inside that, right? So as in containers as an IP netns. So we will create our own containers inside that, and then we will demonstrate that we can actually ping between one container inside worker A to another container inside worker B, right? If everything goes well, that That's what we will do, right? And we'll be using Flannel, which is a very simple basic CNI, and we'll be using VXLAN tunneling. I've asked few of you to install Wireshark. If you can do it, that's very good. We can actually see the packets, you can actually see the tunneling happen. So yeah, let's get started. So again, simple, create two folders. There'll be a number of config files we'll have to create for this. So just create two folders, A and B, and run these two, essentially workers, right? I'll tell you what is happening in this command. This is privileged flag, which will allow you to do all of you're running sudo ipnetns commands today, right? So to be able to do that from within containers, we need to have this privilege. This is the volume mount we were talking about yesterday. We are mounting a folder A on the host Linux into the container so that we can change things inside, see the results outside. And what you're seeing here is an image that we have created with all the dependencies packaged inside for you, right? There are a number of different tools that you need to run. So all of this is packaged inside this container so that you don't have to install them, right? This is a classic demonstration of what Docker gives you, right? You're packaged it. We'll have a bunch of terminals in this session, so figure out a way to organize this stuff. We'll have say 2 for every command we run, right? We'll run it on worker A and then worker B, right? 2 terminals gone there, and so on and so forth. Do we have the workers running? Is the image pulling?
Downloading.
So the PDF is shared on the Slack. Please use that to get these commands because they are very big and you might miss some step and it might create issues later. Thanks.
So if you're just waiting, I can just chit chat. So this is, if you see this is GitHub's container registry, right? So Docker, the format is different from Docker the company, right? So Docker the company runs its own registry, which is where we were pulling from yesterday. The default images get pulled from there, but every company has their own registry offering. So the Red Hat has something called Quay, Google has something, so on and so forth. This is GitHub's container registry, and because it's GitHub, you have namespaces, right? So this is our IBM organization, and this is the repo, right? And then this is the tag. So if you go to this repo, you can actually go to github.com/ibm/this thing. You can see the Docker file that I used to make this Docker image, right? And if you see, that's a very large Docker file. There are a lot of steps. So because I have done that, it's easy to just give you the thing instead of giving you all those steps. Okay, so apparently there is a length restriction on the container name. It can't be single letter, so you can just make it worker A or something like that.
Please make sure the container name is WA and WB. There is a typo here. So --name WA --name WB. Otherwise the container won't come. It will throw a container name error.
If you're already running the command, if it's already pulling, don't disturb it. You can change the name later, that's fine. The command will fail and then we can try again, but the image will already be pulled. So just remember this exec command, we'll have to use it a few times to run things. So if you have the 2 workers running, you probably already have a bash. You have a bash shell there, right? So you can just run the first command on that shell and then use create new shells. Okay, so I'm just skipping this because this is an instruction if you are going to run it on 2 machines. So the first step we're going to do here is run something called APC, right? But before we run, I'll just give you a quick intuition of what is this and why is this needed, right? So it's a distributed key value store. So Kubernetes relies heavily on it. Almost all of the components in the Kubernetes ecosystem rely on ATC, right? But why, right? So firstly, what is a key value store? Let's start there, right? So you've obviously all heard of tables and SQL databases and traditional database, right? So the last 20 years we have a lot more kind of database types is not just tables. We also have things like document stores, we have things like columnar stores. So all of these are designed to optimize certain kind of use cases, right? So one of this is this family of key value stores. It's very simple actually. You want to set a key and get a key, right? That's the kind of API you want to expose, and then you can just do that in number of keys, right? That's literally the API. There is no tables, there is no relation, there is no schema. You're not really designing anything upfront. You can write a key, you can write any value, any string value into the key. That's it, right? So, but the challenge really is in the distributed part of this, right? So if you just run one node, one key value store, that is like something that is easy to do, right? But once you have multiple workers, multiple machines, essentially the idea here is you want to replicate the data and you want to replicate the processing of the data so that the system is fault tolerant, right? This is a very big area of research in distributed systems. All of distributed systems revolves around this. How do you drive consensus when you have multiple machines trying to do the same thing? So the problem here is faults, right? So anything can fail. A worker can fail, network can fail, things can be slow, machines can get hacked, right? So then really what you want is you just want a globally consistent view for the keys that you're writing and getting, right? So you write a key, you want that value to remain, right? No matter what happens to operating system. If you had only one worker, if it crashes, that key is gone. That's the kind of thing you're trying to avoid, right? But just adding more workers is not enough. There has to be a complicated protocol that runs between them called consensus. You can look into this if you're interested. This is a full area of research in distributed systems. So etcd is a very simple, it has a simple protocol inside to manage this consensus. You don't have to worry about that right now. But all you need to know is in Kubernetes, every control plane worker has an etcd replica running, and they all talk to each other in the background. And you can write, you can set and get values, key values on any one of them, and the view you will get will be a unified view. It's as if you're writing and getting from a single box, right? And I'm mentioning this because this is the first step towards getting our networking running, right? Why? Because we have different workers in a cluster which have to network, and they have to manage the metadata between them, right? For instance, IP addresses. So we want to ensure that no two containers get the same IP address, right? But these containers are running on different workers. So how will the workers know what IP addresses have already been used or not used? So to communicate information like this, they rely on etcd, right? So Frana also relies on etcd. So what we're going to do is we're going to run a simple 2-node etcd cluster in our setup. We have 2 workers. So you have to get the IP addresses of both the workers on both the other part, right? Once you do that, you can essentially run etcd. So this is the actual command. It's really big. Just copy paste it. I will explain what it is, but just copy paste it and ensure it's working. Before you run these 2 commands, you need to set these environment variables, right? I hope you understand what is going on here. We want to run etcd on 2 workers. We want them to talk to each other, so they need to know each other's IPs, right? So worker A, you can essentially set up local is your own IP. So what is your IP? You can find it using hostname -i command, right? And you can run the same hostname -i command on your worker B, and use that as the essentially set the environment variable other on the first A to ensure that they can talk to each other. You have to do the same thing on both places, where local refers to themselves, other refers to the other end. So do this in the 2 shells that you have, right? Use hostname I on both places, get the 2 IPs, and essentially manually share the IPs between these 2 places. Ideally, if you're running, okay, it depends on how many Docker containers you're running. Can somebody just tell me an IP of worker A that you're seeing when you run hostname I? 0.2, okay. 0.4, okay. So on the 2 terminals that you already have running, ensure that you run these 2 commands with the right IPs. In this setup, everything we will do will be within those 2 containers. None of the commands, you don't have to run any command on the host, it will be within one of these 2 containers. So just to be clear, right? So you'll be running the export command 4 times. 2 on worker A, 2 on worker B, right? In both the workers, local should refer to its own IP, other should refer to the other one's IP. So are people able to run the etcd? For some of you it's running, right? You're able to run this thing. Can you go to the next one and verify that it's working for you? Run this command inside one of the two workers and confirm that it's connecting to each other, right? So here this A is actually just the name of the etcd process, right? Not the worker process. So it's fine. It can be different from your worker. Are people able to see this? Does at least any one person have this running? You have the member list, you're able to see both? Good. That means your cluster is healthy, your ETC cluster is connected, they're both talking to each other, which means you can actually go to the next slides and try to write keys and read keys from this. Okay. How many of you have tried this? Those who have the cluster ready, you can just go ahead and try this. So those who are already ready with the cluster, you can kind of put this JSON that we have here into a file. You can just put it into any one of those two folders that we created, A and B. Just save it as flannelconf.json, right? This. You can use your local PDF and copy paste. I will just go back to this. One second.
After putting this command, we are getting
something has gone wrong. Invalid value HTTP, something has changed. You do one thing, you copy it from this, right?
Yes.
There is some problem with that command, add some new lines. I've asked him to give the cleaner command. One second. Is this command on, you put it on Slack? Someone else did it. So just check Slack, same command is there, you try to copy paste from there.
this command is expected out. Yes, sir.
No, something is not working. I think. See, I think that's what. Don't copy paste this. Control C and copy paste the same thing from Slack.
Slack.
On Slack, same command has been shared without the problems. One second. Yeah.
So these both have been connected. Now to run this command, I have to connect again
exec into one of those. A worker A or worker B.
How should I?
Docker exec IT interactive terminal worker A WA dash space dash. Yeah, that's it, right? So you will get.
Now I can run.
Yes. Actually, no. Before doing this, run that command. The previous slide. This one. Yeah.
No process I'm using.
Yeah. I think it's a firewall thing. That's what I think. Yeah. So you're good, right? So it is essentially showing the cluster is ready. One of them is a leader, and now you can go and see that the key value stores work. Show of hands. Okay. We are in a reasonable state. I'm going to go proceed. So you're able to write and you're able to get keys, right? So this is showing that the key value store is working. Right? So how will we use it? Why did we do all this, right? Why did we do all this thing? Because Flannel is going to use it to save the configuration and distribute it to all of its workers, right? Essentially all the Kubernetes nodes. So on the left you see is a sample configuration that we have for Flannel. You can use the exact same thing. But you can see that we are actually choosing some things here. We are actually saying we want the network.
To create this file, we should have used NAT.
We are saying that we want a network subnet of 11.series, right? So essentially this is what eventually Flannel will use to assign to all of our containers that we create on the cluster. And similarly we are saying the backend that we want to use to connect between workers, VXLAN. As I was talking about earlier. This is the VNI, just an ID that it uses. If you change this, you will see the change reflected when you finally create and examine the packets, right? Right now it will be 100. If some of you want to change it, you can just maybe change it to 101, 102, it will still work. Don't change the port just for ease of use. So we will just write this configuration as a file and then I just save it as this for convenience and then load it into etcd, right? At this key. So essentially in this story, this is the key. For legacy reasons, this is the key. There's no reason why it has to be this, but for now just go with this key and feed this JSON as the value. Right? If you run this will now get loaded into Flannel and all the workers will get it. So you have to do it in only one place, right? Any one of the workers is enough. You don't have to do it twice. So how many of you have already done this? How many of you have it loaded? Okay, good. So you can also hopefully see the use of the volume mounting we have done, right? The volume mounting A and B folders that we have. It's outside, you can edit files directly there and you can go into the content. So for those going through the slides, right, there are a number of slides with installation instructions, right? So you don't have to do any of that. They're all already done inside the Docker image. So there's a slide 26 on installing Flannel. You don't have to do that because that's why I gave you the Docker image, right? So Flannel will already be there. You can directly run the commands. Are people able to run this command? So once you're done with loading the config, you can run this again as before using docker exec on both places. If you run the command that is shown here on the left, it should run like this, something like this, and it should create the subnet.n file, which should look something like what's shown on the right.
Mismatch is happening between these two, like two machines.
But it's still working after that?
No, it's not like.
The member list command also is not working?
No, I have not tried that.
Try the member list command, that's the only way, etcd control member list. If that works, this is just a warning. If that doesn't work, clear out those two a.etcd folders and retry. That's all. It's just that cached older cluster. Yeah, that's Have few of you reached this step at least? Are you able to see this output on the left? Show of hands. One, few. Okay, pretty good. So essentially, this is important because you can actually see here it's Flannel running for the first time on that worker. It has done the basic setup, right? And it has also actually at this point created a Flannel 0 interface. So if you just open one more terminal on the worker, on both workers, and do an if config, you will see a new Flannel 0 interface, and that would have an IP in this external range. So that Flannel 0 interface will be used to actually set up the tunnel between the workers. That's the use. So if you have reached this step, right, so what you're doing is you're asking Flannel daemon to run on each worker. You're asking it to run, right, at which point it will connect to the etcd, get that information about whatever we have fed in, which is that 11.series IP range /8, etc., and come up with some configuration for just for this worker, right? So this is essentially will be used in the future for creating containers on this worker. So if you see here, this first line is the full network which you specified. The second line is a subset of that, right? It's a subnet within that network for just for this worker. So it creates a subnet for each of the workers. So that way, it's a very simple way to ensure that containers don't get the same IP, right? So now this worker can freely assign any IP within that subnet range, and it will not conflict with any other containers IP on any other worker. And because it is managing containers on one machine, it can obviously take care of not repeating this. Okay, so those who have already reached this stage, you have to create a new folder. So essentially in that same folder A, create a folder called netconf path and dump this there, okay? Dump this file there. Okay, so if you have problems with this file, there is a better version on Slack. Google Drive has mangled some of the double quotes. Just use the version on Slack instead. Copy, use it. Have some people crossed this? People have reached this stage and crossed this stage? Good. So can you try creating a container? You're able to do it? Are you able to see the IP? Are you able to ping? Oh, very nice. Okay, we have at least one person who has reached the end-to-end setup. So the point is once you reach this stage, right? So you are essentially creating a new namespace. It's empty, and then here you're asking Flannel to actually take care of it. Do everything we did in the morning manually, automatically. So at least some of you are able to ping between two containers. So essentially, this maybe just gives you an eye level of what is happening underneath, right? Okay, I think we have to break for lunch now. We have anyway run out of time. Some of you are able to get to the ping state, so that's great. We should have kind of simplified instructions further, but it's all a learning, right? So this is, if you see the, just for understanding, this is how it looks like at the end of the day, right? So you have the VXLAN header, which will carry the packet, inner packet inside an outer packet. So these lines are color coded. Right? Between the worker, what goes is a green packet. So if you run Wireshark successfully and if you're able to capture packets here, you can actually see this outer Ethernet, and because Wireshark can dismantle stuff, it can actually look and it will figure out this inner stuff. But if you do a Wireshark capture here, you will actually only see the normal packet because it's not yet encapsulated, right? So Flannel is set up everything so that when the container pings, the packet will first go here like before, and then at this point it gets the encapsulation process, and then it goes out as this green packet, right? So this green packet is a normal packet which has, just from the outside if you see, you will not see any container information or anything, right? It's just a normal packet. On this side again, it will go through a particular port. This is a port that we have specified in our configuration, 8472 or something. And this is like, once it gets here, again, the Flannel has set up the configuration to read the packet, right? So that's how this is the tunneling process that is working. So the people who have not finished the commands, you can just try it offline. You can also try to run Wireshark at different stages and you can actually see the packets in that different form. Okay, so I think we should break for lunch. Thank you.